Hello, my dear 7th standard students. I am absolutely thrilled to have you in my class today. Grab your notebooks, sit up straight, and get ready, because today's high-energy explainer is going to help you master absolutely everything you need to know about our Earth. We are going to make sure you get full marks on your upcoming social science exams for sure. Okay, let's dive right into this.
Here is our agenda for today's explainer. First, inside our beautiful Earth. Second, peeling the Earth's layers. Third, rocks, minerals, and ores. Fourth, igneous, the primary rocks. Fifth, sedimentary and metamorphic rocks. And finally, number 6, the never-ending rock cycle.
All right, kicking things off with Section 1, Inside Our Beautiful Earth, the Mystery Beneath Our Feet.
Now, I want you to ask yourselves a very logical question. Why can't we just grab a massive shovel and dig down to the very center of the Earth to see what's actually down there? Well, first of all, our beautiful Earth is incredibly old. We are talking about a massive 460 crore years old, and its surface has been constantly changing throughout all those years. But geologists tell us that our direct knowledge of the inside is actually pretty limited. We live comfortably right up here on the surface, but the deep interior, well, that remains a bit of a mystery. And here is the exact reason why we can't just dig our way down. Heat, the extreme heat. As you go deeper, the temperature increases rapidly. At the center of the Earth, it's estimated to be a scorching 5,000 degrees Celsius. It is so unbelievably hot that literally no machine and certainly no human could ever survive it. So because we cannot access it directly, we have to rely on clever indirect clues, like the behavior of earthquake waves and the density of rocks, to figure out what's hiding inside our planet.
Moving right along to Section 2, peeling the Earth's layers, just like an onion.
Listen carefully, students, because this is an absolute goldmine for your exam preparation. The Earth is constructed in 3 concentric layers, exactly like peeling a giant onion. Take a mental screenshot right now. First, we have the crust, which is also called the lithosphere. It's the thin, solid outermost layer. It's about 35 kilometers thick on the continents and just 5 kilometers thick under the oceans, with a density of about 3.0 grams per cubic centimeter. Just beneath that is the mantle, a very thick 2,900 kilometer layer full of dense, hot magma. Finally, at the very center is the core, or the barosphere, that has a huge radius of 3,500 kilometers and a super high density ranging up to 13.0 grams per cubic centimeter.
Now, let's zoom in on the crust for a quick second. I want you to mark this crucial mnemonic in your notebooks. It's a genius exam hack. The upper continental crust is known as Sial. Why? Because it's made mostly of silica and alumina. But the thinner, lower oceanic crust is called Sima, because it's made of silica and magnesium. So you have Cl and Sima. It's a brilliant, simple way to remember their chemical compositions.
And if we go all the way deep down to the core, we find something very similar. The core is made up of heavy metals, and we call it Fe. That stands for nickel, which is Ni, and iron, which is Fe. This heavy metallic wake-up is exactly why the core is the absolute heaviest and densest layer of them all. Okay, on to Section 3, rocks, minerals, and ores, the building blocks.
So we know the layers, but what are the actual building blocks made of? First, you absolutely must know the definition of minerals. Minerals are naturally occurring solid substances present in rocks that possess a definite chemical composition. Unlike rocks, which are kind of just a random mix of materials without a strict recipe, minerals are chemically precise. They are the true ingredients that make up the rocks around us.
And this perfectly brings us to ores. When a rock is heavily packed with a large percentage of a specific valuable mineral, it officially becomes an ore of that mineral. This is huge because this is exactly where humans set up commercial mining operations. We don't just mine anywhere, we specifically target areas where these ores occur.
Let's move to Section 4, igneous, the primary rocks, born from fire. Now pay attention to this magic trick of nature as we learn about the 3 main types of rocks. The word igneous actually comes from the Latin word ignis, which literally means fire. Why? Because these rocks form when hot magma cools down and solidifies. And this beautifully illustrates the 2 main types of igneous rocks, intrusive and extrusive. Intrusive rocks cool very slowly deep inside the earth, giving them large crystals like granite. Extrusive rocks, however, erupts right onto the surface and cool very rapidly, creating fine-grained crystals. Basalt is a perfect example here, and in fact, our very own Deccan Plateau in India is entirely made up of these extrusive basalt rocks.
Now, you are going to want to remember these characteristics for your exams. Because they were the very first to form, igneous rocks are known as the primary rocks. They are very hard and compact. They do not occur in distinct horizontal beds or strata. They contain zero remains of animals or plants, which makes sense since they come from boiling magma, right? They don't allow water to percolate or pass through them easily. And most importantly for us, they're the primary source of your precious and valuable minerals, like gold, silver, iron, and aluminum.
Next up, Section 5, Sedimentary and Metamorphic Rocks, Layers and Transformations. We know how primary rocks are born, but what happens when rain, wind, ice, plants, and animals slowly break those rocks down over thousands of years? Well, those tiny rock fragments are carried away and deposited in depressions as sediments. Over time, they compress and harden into sedimentary rocks. They are incredibly widespread, covering about 75% of the Earth's total land area. Because they form in horizontal layers, mostly underwater, they do something truly amazing. They trap the remains of ancient plants and animals between their layers. These preserved remains are what we call fossils. Let's compare those sedimentary rocks with our third type, metamorphic rocks. While sedimentary rocks like sandstone, salt, and coal build up gently in softer, horizontal layers, metamorphic rocks undergo a totally violent transformation. When existing igneous or sedimentary rocks are pushed deep underground, they face extreme heat and pressure inside the earth. This intense environment completely alters their original color, hardness, texture, and mineral makeup. They are permanently changed into metamorphic rocks. And finally, Section 6, the never-ending rock cycle, nature's ultimate recycling. Let's tie all of this together into one continuous geological dance. The rock cycle never, ever stops. Think of it like a giant recycling plant. First, molten magma cools and solidifies to create igneous rock. Over time, that rock breaks down into fragments, washes away, and compresses into sedimentary rock. Then, as the Earth shifts, those rocks get pushed deep underground, crushed, and heated by intense pressure, transforming into metamorphic rock. Eventually, they can melt right back into magma, and the whole shebang starts all over again. Remember this fundamental truth. The rock cycle is a continuous process that describes the formation, breakdown, and reformation of rocks on Earth's surface. This constant reformation through various geological processes is exactly what keeps our 460-crore-year-old Earth so dynamic and ever-changing beneath our very feet. It's a beautifully designed system.
My dear students, structure is the key to memory. We have covered a massive amount of crucial ground today, from the cial and sima of the crust to the fascinating stages of the rock cycle. I highly encourage you to replay this explainer and listen to my teachings anytime you need to perfectly recall these concepts. Come back to it again and again until it's permanently lodged in your memory for exam day. But before you go, I want you to look down at the ground beneath your feet and ask yourself, what phase of the rock cycle is happening right under your shoes at this very second? Keep studying hard, stay curious, and I'll see you in the next class.
Hello and welcome, my dear 7th Standard students. I am absolutely thrilled to have you here today for this ultimate masterclass explainer on social science. Today, we're going to tackle the composition and structure of the Earth, and I promise you, by the end of our time together, we are going to uncover every single exam detail layer by layer. So grab your notebooks, sit up straight, and let's get ready to learn.
Okay, let's dive right into this. Here is your perfect syllabus blueprint for securing top marks today. Number 1, the Earth's 3 layers. Number 2, rocks versus minerals. 3 types of rocks. 4, the continuous rock cycle. And 5, secrets of Earth's interior.
Section 1. The Earth's 3 layers, peeling the giant onion.
Now I want you to think of our planet kind of like an enormous onion. It's divided into these distinct concentric layers resting one inside the other. Pay very close attention here, students, because this is a highly probable distinguish between question for your exams. We need to clearly contrast the crust and the core. The crust is that solid outermost layer, literally the very ground beneath our feet. Geographers also call it the lithosphere. And you know, it's actually quite thin. It's about 35 kilometers thick over the continents, but only 5 kilometers thick under the oceans, with a relatively light average density of 3.0 grams per cubic centimeter. Now, on the complete opposite end of things, we have the core, lying deep right at the center of the Earth. We call this the baryosphere. It is absolutely massive, with an average radius of 3,500 kilometers, and it's incredibly heavy, boasting a density ranging from 5.0 all the way to 13.0 grams per cubic centimeter. So to recap, crust is the thin, light lithosphere on the outside, core is the giant, heavy baryosphere on the inside.
Let's zoom in on that thin crust for a second.
I have a fantastic teacher's trick to help you memorize exactly what it's made of. We're going to look at two chemical word formulas, Sial and Sima. The continental crust is made of silica and alumina. If you take the Si from silica and the Al from alumina and put them together, you get Sial. The oceanic crust, on the other hand, is made of silica and magnesium. Take the Si from silica and the Ma from magnesium, and boom, you get Sima. So continental is Sial, oceanic is Sima. Write that trick down, I'm telling you, it will save you in the exam hall.
So, if the crust is on the outside and the core is all the way on the inside, what exactly is in the middle? Well, that brings us to this massive number, 2,900 kilometers. That is the thickness of the mantle. The mantle sits perfectly sandwiched between the crust and the core. It's thick, it's unbelievably hot, and it contains rocks in a molten, liquid-like form that we call magma. Because it holds heavier materials like iron and magnesium, its density is higher than the crust, sitting right between 3.5 and 5.5 grams per cubic centimeter.
And dropping all the way back down to the very center, we have to talk about what makes that core so unbelievably heavy. It's made of incredibly dense, heavy metals, specifically nickel and iron. Just like our Sial and Sima trick earlier, geologists combined the first two letters of nickel, Ni, and the chemical symbol for iron, which is Fe. Put them together and you get knife. Knife is the crucial term you absolutely must remember for your fill-in-the-blank and multiple-choice questions. If they ask what the core is called based on its composition, you confidently write down knife.
Section 2. Rocks versus minerals, the building blocks. Now that we know the layers, let's look closely at the materials that make up that outer crust. What's really interesting here is how this naturally structures another essential distinguish between answer for your exams. Lots of people actually think rocks and minerals are the exact same thing, but as top-tier students, you know better. Rocks are simply the general materials that make up the Earth's crust. They don't have a definite chemical composition. And why is that? Because rocks are made of minerals. Minerals, on the other hand, are the specific, naturally occurring solid substances found inside those rocks, and they absolutely do have a strict, definite chemical composition. Basically, think of it like this. Minerals are the ingredients, and rocks are the baked cake.
But, why should we even care about rocks and minerals? Well, I want you to memorize this specific list for those tricky, long answer questions about the utility of Earth's materials in our daily lives. They are incredibly useful. Igneous rocks are basically treasure chests providing valuable minerals like iron, gold, silver, and aluminum. Sedimentary rocks are where we find our crucial fossil fuels, like the coal which powers our homes. Rocks give us our grand building materials, granite, marble, and sandstone, used in everything from ancient historical monuments to your very own kitchen counters. Minerals drive our modern industries, and nearly all of these precious resources are generously supplied by that super thin outer crust we just studied.
Section 3. 3 types of rocks: igneous, sedimentary, metamorphic.
All right, geologists categorize all rocks based on exactly how they were formed. Our very first family is igneous rocks. These are quite literally born from fire, specifically from hot molten magma cooling down and solidifying. But there's a catch. If that magma gets trapped below the surface of the Earth, it cools very, very slowly, which forms large crystals. We call these intrusive igneous rocks. Think of granite and dolerite. But if a volcano erupts and that magma spills out onto the surface, it cools very rapidly in the open air, forming fine grains. We call these extrusive igneous rocks. A perfect example is basalt. In fact, our magnificent Deccan Plateau here in India is famously made almost entirely of extrusive basalt rocks.
Next up, we have the sedimentary rocks. Let's walk through these specific traits layer by layer. Over thousands of years, wind, rain, and ice break older rocks into tiny fragments. These little fragments are carried away by rivers and deposited in flat layers, usually underwater. Because of this process, sedimentary rocks are generally softer than igneous rocks, and they form in very distinct horizontal layers. If you look closely at some of them, you can even see ancient marks of water waves or dried mud cracks. More importantly, as these layers slowly built up, ancient plants and animals got trapped inside, which is exactly why sedimentary rocks are the only rocks that contain fossils. They're everywhere, covering about 75% of Earth's land area. And they can form mechanically, like sandstone, chemically, like salt, or organically from plant matter, like coal.
Our final family is the metamorphic rocks. Now, the word metamorphic literally means change. These rocks were once just ordinary igneous or sedimentary rocks, but they got pushed deep, deep inside the Earth. Down there, they were subjected to excessive, crushing pressure and intense heat. This extreme environment completely changes their original properties, their color, their hardness, their texture, and even their mineral composition. It transforms them into something entirely new and often incredibly beautiful. For example, plain old sedimentary limestone gets squeezed and heated until it magically transforms into stunning, hard marble. Soft shale gets compressed into tough, durable slate.
So, the absolutely crucial point here is knowing which rock belongs to which family. I want you to treat this classification as your direct exam cheat sheet. Take a mental snapshot right now. Igneous includes granite, dolerite, basalt, and pumice. Sedimentary includes sandstone, limestone, coal, and shale. Metamorphic includes marble, slate, quartzite, and gneiss. I actually highly recommend pausing this explainer if you need to and copying this exact table into your notebooks. It is guaranteed marks, for sure.
Section 4. The Continuous Rock Cycle, Earth's Recycling System.
And this brilliantly illustrates that these rocks don't just stay in their categories forever. Our Earth is actually a massive, non-stop recycling system, where one type of rock is constantly transforming into another. Let's trace this cycle step by step. Step 1. It all starts deep underground, where hot magma eventually cools and solidifies to form strong igneous rocks. Step 2. Over millions of years, the elements of nature, running water, wind, ice, even plants and animals, break those hard igneous rocks down into loose fragments and sediments. Step 3. These loose fragments are carried away and deposited into depressions like riverbeds or oceans. Under the immense weight of the water, they are compressed and hardened into layered sedimentary rocks. Step 4. Eventually, shifting landmasses push these sedimentary rocks deep back into the earth, where excessive heat and pressure bake them, changing them into metamorphic rocks. And if they get pushed down even further, well, they melt right back into magma, and the whole amazing process starts all over again.
Which brings us to one of the most poetic and scientifically accurate facts in geography. Say it with me, students. The rock cycle has neither a beginning nor an end. It is a strictly continuous, cyclic manner of transformation. This quote is a fantastic, punchy sentence to write at the end of a long answer question to really impress your examiner.
Section 5. Secrets of Earth's Interior, Solving the Mystery.
So we have learned so much today about the deep mantle, the heavy core, and rocks melting deep underground. But how do geologists, the brilliant scientists who study the Earth's interior, actually know all these facts if we can't physically see the core? I want to pose this question directly to you. Why can't we just dig a massive hole, build a super strong elevator, and travel to the center of the Earth to look at it ourselves? What's really stopping us?
Well, the answer lies in this staggering number, 5,000 degrees Celsius. As you travel deeper and deeper into the Earth, the temperature increases drastically with depth. By the time you reach the center, the estimated temperature is about 5,000 degrees Celsius. To put that into perspective, that is almost as hot as the surface of the sun. It is absolutely impossible for any human or any machine to reach the center due to this intense, extreme heat and the crushing physical pressure.
Because we cannot physically dig that deep, geologists must act like detectives. They rely entirely on indirect evidence. They study the density of materials found near the surface and calculate the mathematics of the planet's mass. But their biggest tool by far is analyzing the behavior of earthquake waves. When an earthquake happens, it sends shock waves through the entire planet. By measuring how fast and in what direction these waves travel through the ground, scientists can essentially take an X-ray of the Earth. For instance, these earthquake waves have revealed that the Earth behaves like a solid body up to a depth of about 2,900 kilometers from the surface, which, as we learned earlier, exactly matches the boundary of our crust and mantle.
It is truly mind-blowing to think about, isn't it? Despite walking, playing, and standing on its surface every single day, the deepest, most extreme secrets of our Earth remain hidden miles below our feet, understood only through the incredible deductive science of geology. I really hope this explainer has made the composition of the Earth crystal clear for you all. Remember, repetition is the key to top marks. I warmly encourage you to come back and listen to this session again and again, anytime you need to revise for your exams. My teachings are always here for you. But before you go, think about this. If extreme heat and pressure can turn soft shale into durable slate, what undiscovered beautiful rocks might be forming deep beneath us right at this very moment? Best of luck with your studies, my dear students, and keep exploring.